Thank you for the invitation and for your presence. I'm Professor Liz Holm from Carnegie Mellon University, but I have a connection to all of you that's deeper than that. I'm a 20-year veteran of the U.S. Department of Energy, one of the national labs there. And it was my privilege to work for the United States in that capacity. When I started my second career as a professor, I came to Carnegie Mellon as a place that was a node, a hub for both artificial intelligence, computer intelligence, as I call it, and my field, material science and engineering, and then one of the core engineering disciplines. One of the things that has been exciting for me was if I thought I was going to academia to be in an ivory tower to get out of the engineering milieu that I had inhabited for the last 20 years, I was wrong. I get calls weekly, sometimes daily, from industries at the local, regional, national, and international level, wanting to learn about, wanting to apply, wanting expertise in the application of data science, artificial intelligence, computer vision to their missions, both in advanced manufacturing and in conventional manufacturing. It's a booming area, and it's an area that we have a chance to leap ahead of our economic competitors. And so it's a privilege to be here to talk about that. But I'm going to start out, as professors must, with a bit of a lesson. And we've been talking a lot about 3D printing, additive manufacturing. And it's a new kind of manufacturing. It does things we can't do any other way. I have a little part printed in a 3D metal printer here. You're welcome to look at it after the talk. It happens to be the logo of our Additive Manufacturing Consortium, and you'll notice it's got lots of little features printed in it. This could not be made any other way. It couldn't be cast, it couldn't be machined, it couldn't be forged, it couldn't be stamped. It had to be made on a bit-by-bit basis, as one does in 3D printing, because there's all these undercuts and 3D components that you just couldn't do any other way. So this opens up a new manufacturing sphere entirely. It's important for healthcare. You want your hip joint to be your hip joint, right? You want them to make one that's perfect for you. And that's in the medical area. You want to be able to make small numbers of really good parts. For NASA, for example. NASA doesn't want to make 100,000 or 1 million or 10 million of a part. They want to make the 10 that they need and do it efficiently. And you want to be able to produce parts that you could not produce another way. You want GE to be able to make that consolidation of design that enables them to make one good part instead of having to have 20 parts, all of which individually could be problematic. So this is additive manufacturing. But it's new. And what does that mean? How it's made matters. So here's 2 piles of potato chips. They're golden and crispy and delicious, but they're made differently. The pile on the left, Lay's potato chips, are made by slicing potatoes into thin slices and frying them up. It's so intrinsic to the product that the manufacturing process is shown on the actual bag, right? A sliced potato. That's how they're made. The pile on the right are Pringles potato chips. Pringles aren't made that way. They're made by making a dough, putting it through rollers, and using essentially cookie cutters to cut into Pringles. And so you see them coming out here. As a material scientist, I would say that Lay's potato chips are a wrought product. They're made through machining. And the Pringles are an extruded product, and they are made through an extrusion process. We've all, or at least probably most of us here in the room, eaten both kinds, right? And they are different. They both fill a potato chip niche, but they feel, they crunch, and even taste a little bit different. So they have the same design, they're a potato chip. They have the same ingredients, potatoes, but they have different performance. And the same is going to be true when you make a part with additive manufacturing. So now I want to take you on an imaginary journey. You're now an FAA official, and your responsibility is to approve parts to go on airplanes that fly in the sky that carry you and me around the country and the world. And this is an important job for me personally, to make sure that this works well. I have a fear of flying. So here's an Airbus 380 spoiler, and someone comes to you, they say, I can make a cheaper Airbus 380 spoiler. And I can do it through additive manufacturing. The part on the left, that's the original equipment spoiler. It's made actually by machining a solid chunk of titanium material. But I've 3D printed the one on the right. It's got exactly the same dimensions, tolerances, everything. It looks a little different because I've been able to take a little of that metal out, that they had to include because it was a machine part, but it's exactly the same thing. I made it with 3D printing. It's the same material. Do you approve that to fly? Do you trust that same design, same ingredients, mean the same performance? No. No more than a Pringles is a Lay's, right? You're going to have to figure out a way to say this is okay. And that is one of the areas that artificial intelligence, computer science, data science, whatever term you want to use, comes into play. So let me, now that we have a common basis for understanding why we might need to do something more with data, go on and show you what that might involve. Now, this is the old way. This is how we would have tested that spoiler well, now, in the olden days of now, which is we would just make a lot of them and break them until we understood exactly how they break in different environments, how they break under different stresses, and so on. Here I just show a set of tensile bars. They're just metal rods that have all been broken so that we measure the fracture strength of these bars and we know how strong this particular kind of metal is. So it's a good classic way to do it. And it goes back to that high safety factor that Stefan mentioned for GE. We took a conservative approach. We can't do that anymore. So our new way has to be not breaking 1,000 or 10,000 parts. It has to be something more aligned with the additive manufacturing process itself. So what I'm showing you here is the additive manufacturing process. This is 3D metal printing, and I thought we should actually look at it at least once as we're talking about it all. So what you're seeing is you're looking into the build chamber of the additive machine. That gray stuff is metal powder, very fine metal powder. It's been spread out with a squeegee on a plate. The bright dot, you see, oh, there's the squeegee going by. It's going to give us another layer. Squeegee of the powder. That bright dot you see is the laser. The laser is melting the metal powder to whatever is beneath it. And layer by layer, we're going to build up. So you can see in this case, it's building our consortium's logo in a titanium metal package. The laser's moving around, really hot. If you had sound on this, which you don't, you would also be hearing a lot of sound. You'd be hearing buzzes and flunks and raps. So my point of showing you this in part is to show you what it actually looks like when you start to build up a 3D printed process. But it's also to point out that this is very different from something like forging, where you kind of put a piece of metal in there and it goes whomp. This, we've got data galore that we can extract from this. We can look at the bright spot. We can look at the light data. We can look at the power data. How much energy are we pumping into the system? We can put microphones in the chamber and listen to the sounds, the acoustic information about what's happening, and so on and so forth. We can measure temperatures. We can measure, and we have the design data, the shape data for the part. We've got it all. This plethora, this abundance of data, and that's what we want to use. So that's where AI comes in, or is it sometimes called data science. It's taking a lot of information, Amazon taking every single click that you make on their website and turning it into information knowledge that can be used. So our goal here in my research group is to use computer intelligence to support the human expert in advanced manufacturing processes. And we use computer vision, which is using the computer to intelligently look at images, and we use machine learning, which is the computer learning as data comes in, what the trends are, what the decisions that should be made are. And we're going to do it for additive manufacturing at 3 levels. The level of the raw materials, that's that gray powder that you saw, that's really, really important to the final part. Just like Pringles has to choose the right kind of potato starch in order to make a Pringle. We do it for process control, looking in the build chamber itself, how do we control that process on the fly? And we do it to qualify that final part for the FAA inspector to say that this part coming out of the additive manufacturing build is good. Very quickly, hopefully no technical details beyond what you're willing to hear. Let's start with raw materials. The old way of dealing with raw materials was to take a picture of the raw materials. So those are just it's a microscopic image of those tiny grains of that metal powder. And we turn that into a graph. This is a graph of the sizes of the powder particles. So we took this image that's quite complex, has a lot of information, and turned it into something quite simple, which just talks about size. And that's not enough. That's not enough richness to understand how these powders behave. And so our new way, using computer vision, we take the same image, but we have the computer identify every single powder particle and examine it and understand it. Is it crunchy and rough? Is it smooth and round? Does it have satellite particles attached to it? And the computer then learns what powders look like, and it sorts each particle into its own class. And we end up with this data cloud of particles. Each of the little tiny boxes up there on that background image is a picture of one particle. one tiny, tiny microscopic particle of powder. There's over 40,000 of them in this image, but our actual data is hundreds of thousands. Then it becomes black on the screen. And if we look, they're sorted by the type of particle, size, shape, crunchiness. So the upper right, the blue box there, is a bunch of particles that are small and round and smooth and good and well-behaved. And the red box are a bunch of particles that aren't. They're big and crunchy. They have lots of agglomerates. They're rough. And those bad particles affect the behavior of the powder when you put it into the machine. They affect how well you can build your part. And so with this data that goes far beyond size, we can do more with additive manufacturing. And that's the theme of my research group. Build monitoring, looking in that box where we saw the laser making our logo. The old way of doing this would simply be to monitor the process, typically with a human, sometimes with a simple video monitor. Here we're looking in and we see something. You can actually see if you look closely. This is the powder bed, and you can see some streaks. Those are bad. And you can see some washboarding for exactly the same reason that a dirt road washboards. When the squeegee goes across, it gets a little bounce going in washboards. And the human expert hopes to catch these problems and do something about them. But again, that ignores this abundance of data. So the new way aggregates all the data. We take the powder bed image. Here it's been pre-processed a little. We superpose it with the actual design that we intend to make, because there's important data about geometry there. We superpose that with a direct identification of defects using computer vision. And then we stack the layers up with each other to actually create a 3D image of what we expect our part to build like. And this is actually a fan blade, and that purple stuff, that's bad. We expect this part to build with some failure in the purple area. And then, of course, to make sure we're getting it right, we compare to a real build. And we find out that, indeed, in that purple area, we see that the fan blades did not build properly. We end up with a defective part. So our goal here is to predict problems and fix them before they occur. Part qualification, the FAA problem, the old way. And this is a company I work with in, this image is due to a company I work with in Pennsylvania. They're a regional manufacturer of metals. I can't use their name. They've asked me not to because they don't want to be associated with defects in their product. But they are kind enough to let me use their images. And they asked us, they said they have a person, a person who's a metallurgist with an engineering degree, who spends his day taking samples of their material, polishing them up, looking at them in the microstructure, literally scanning through to find a defect like the one on the right-hand side there. And when he finds the defect, he takes a picture, and goes back to the shop floor and figures out why this defect occurred and what to do about it. Scanning through micrographs, as they're called, these images, is a really boring job. Finding and fixing defects is a really exciting job if you're an engineer. So they want him to work on the exciting and important part and leave the scanning to someone else. And if there's anyone who's good at doing really boring jobs, it's a computer. And so they came to my group to ask that. And so what we have done is we have a system that we have put together with computer vision where they tell us what the desired structure should look like, and they send us pictures, or in our case, they send us samples, and we take pictures, and we find the pictures that meet specifications and that are fine, good to go. This is a batch of material that is fine. And we find defects of all different kinds. And those defects may or may not be bad, but that's up to the human expert. That's where the human expert gets to do his job more efficiently, with more knowledge and more support. So the human expert spends his or her time fixing the problems instead of just looking for them in a rote way. And that's the part qualification part. I imagine that you could imagine now that the FAA inspector says to the part supplier, well, show me what the substructure of this part was. Show me if the microstructure, as we call it, the substructure, is adequate for the job. Show me a picture and let me put it through my system. And that is one of the steps, at least, in making sure that the new manufacturing process is producing something that we can understand, predict, and rely upon. I'll finish with just a couple of observations. Coming from a government agency, it's kind of new for me to suggest that there are some policy-based objectives, but I'll just say a few. Obviously, there are strong opportunities for artificial intelligence and additive manufacturing, no question. And right now, the U.S. leads the world in both of those fields, both in AI and in advanced manufacturing, 3D printing. That's not a situation that's going to last. Our competitors are nipping at our heels. This is technology that is exciting the world, and the world is going to pursue it. To capitalize on this, to keep it going, we need 3 steps, and it's almost motherhood and apple pie, something you probably hear to the cliche in Washington, D.C. But that is, we need the R&D support. We need to keep our science and engineering edge on this. We need to develop our workforce. This is an opportunity to open up entirely new kinds of positions at all levels, from shop floor up through design and up into the research and development areas. And finally, to do this, we're definitely going to need to be strategic about our partnerships in ways that sometimes come hard to us but should become standard, particularly partnerships between industry and government, industry and academia, because that's what's needed in order to bring this to the world level. So, thank you very much for your attention.